Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Jiangxing Jia. Today we'll study Chapter 2, Fundamentals of Automatic Control, Basic Concepts and Requirements of Automatic Control Systems 2. In automatic control systems, basic concepts and requirements form the foundation for analysis, design, and application. They are crucial for ensuring system efficiency and stability. This lesson focuses on mastering these fundamentals. We will interpret the concepts, explain the requirements, and use case studies to illustrate their application. 1. Classification of automatic control systems. 1. According to the pattern of set point, they can be classified as fixed-value control systems, follow-up control systems, and program control systems. 2. According to the response speed of the controlled variable. They fall into two major categories: process control and servo control. 3. According to whether the control system has a closed loop. They can be categorized as closed-loop control systems and open-loop control systems. 4. According to different controlled variables. They include temperature control systems, flow control systems, pressure control systems, liquid level control systems, composition control systems, speed control systems, position control systems, etc. 2. Performance requirements for control systems. Common performance indicators used to evaluate the quality of a control system are defined based on its dynamic process. The basic performance requirements for control systems include three aspects: stability, speed, and accuracy. 3. Transient process of control systems. Under step disturbance, the control system may exhibit several basic types of transition. 1. Process of sustained oscillation. The controlled variable oscillates around a certain steady value with a constant amplitude. This indicates that the system cannot stabilize after step disturbance and is generally not adopted. Only in processes where fluctuations within a certain range are acceptable and control quality is not critical will this form of transient process be used. 2. Process of divergent oscillation. This indicates that after step disturbance, the controlled variable not only fails to return to the set point, but deviates further and further, possibly exceeding production limits, and even causing accidents in severe cases. This is an unstable transient process and should be avoided as much as possible. 3. Process of damped oscillation. The controlled variable oscillates around the steady state value and stabilizes after 2 or 3 cycles. This is a stable transient process and is often desired in process control. 4. Non-oscillatory monotonic process. This indicates that the controlled variable eventually stabilizes and is a stable transient process. However, compared to damp oscillation, it has slower return speed and takes longer to reach equilibrium, so it is generally not preferred. In summary, the transient response of an automatic control system should ideally be a gradually stabilizing process. This is the basic guarantee for meeting production requirements. Therefore, in most cases, a damped oscillatory adjustment process is adopted in response to disturbances. 4. Transient process and performance indicators. Performance indicators expressed by the step response curve are defined as follows. Maximum deviation. In a fixed-value control system, it refers to the difference between the peak of the first wave of the controlled variable during the transient process and the set point. In follow-up control systems, the overshoot is typically used as the indicator. Damping ratio refers to the ratio of two adjacent peaks in the same direction on the transient process curve, i.e., B1 to B2, usually expressed as n to 1. The smaller the n, the lower the damping. The larger the n, the closer it is to a non-oscillatory monotonic process. When n equals 1, the transient process is a sustained oscillation. When n less than 1, it is a divergent oscillation. When n greater than 1, it is a damped oscillation. When n approaches infinity, it is a monotonic process. For ease of operation and management, a damping ratio between 4 to 1 and 10 to 1 is generally preferred. Regulation time refers to the time taken for the controlled variable to return from the transient state to the new steady state, that is, the duration of the entire transient process. Theoretically, it takes infinite time for the controlled variable to reach a completely stable state. However, it is commonly accepted that once the variable enters and stays within plus or minus 5% of the new steady state value, it is considered to have stabilized. Thus, the actual transient time is the time from the start of the disturbance until the controlled variable stays within plus or minus 5% of the new steady state value. Steady state error refers to the difference between the new steady state value of the controlled variable and the set point at the end of the transient process. That is, E at infinity equals Y at infinity minus Y sub s. In a control system, steady state error reflects the control accuracy of the system. Oscillation period refers to the time interval between the first wave peak and the next wave peak in the same direction during the transient process. Under the same damping ratio, a shorter oscillation period is preferable. That concludes this lesson. Thank you for listening. See you next time.